Hi there, my name is Manish Yadav and this is my first video for EMAC 303 extra credit video. So today I'm going to do the introduction of Runge-Kutta method. So these are the functions and methods are used for the solving first order ordinary differential equations that we talked about before. We take the term from dy by dx is equals to f of x and y. So I want to show you that how we get the form that used for Runge-Kutta method. Okay, so the form that we used for Runge-Kutta method is yi plus 1 is equals to yi plus slope, which is represented by this, and the time of step size which we used as h. This is the general form of all of the different Runge-Kutta method. And I think it's instructive to see another way this might look and how that look is, let's say, trying to do this for one small step from I to I plus 1. So we can separate this term as dy is equals to f of x and y and dx, and now we can integrate the both side. So from yi to yi plus 1 and xi to xi plus 1, and so we'll get yi plus 1 minus yi is equals to integral xi to xi plus 1 function of x and y with dx. So we can move yi to this side, so this will be yi plus 1 is equals to yi plus integral of xi to xi plus 1 function of x y with dx. So this may look little different, but that one thing that you notice, if it's same, like, then this term might be equal to this one. Well, one way that I can show you that this term is must be equal to this, that truly makes some sense. Like we have slope times distance, so our slope could be like yi plus 1 minus yi over xi plus 1 minus xi. I means that an example of a slope, the difference which is like difference in y over difference in x's. Also h just be an xi plus 1 minus xi. It's just because the h is a step size in x. Sorry, just like, so if we multiply these, so these got cancelled out, and what we get is yi plus 1 minus yi, which is, you can see like yi plus, if we do this thing, yi plus minus y plus 1 minus yi. So this is make some sense. So that's just the another way of saying what we are trying to do here, just that this function, this derivative makes some sense to us. Well, there's another way for making some sense. Like I have a function, I have starting point of a function, and I have slope. So like I have the starting point just because we had to have our initial conditions, and I have slope just because this function, this is our slope f of x, f of xy. So this is our slope. So we have our starting point, we have our slope. So what we need to do is we need to find our the value of next function. It might be like this, or so we can say that we, we are just coming along with this slope. So we can say that this is our next point, like this is unknown distance. So we can say that, hey, this is our new value, because no one knows that what what gonna be our next function, what's gonna be our next value, because a function might be like this or this. So that's like just step along, and the slope, that's going to be a pretty good, like this is our y function, what we are trying to get, and we are just don't have it. So this might be a pretty good guess. So that's the idea behind all all over the range Kuta method, that we are taking a slope and moving along with that slope. So the only difference between each method, that which slope, like who can be come up with our estimate with our slope again. So this is the general equation used by range Kuta method. Like we range Kuta method take this equation as a general equation.